Hello, this is Little Pig Team 2's final technical presentation. Hello, I'm Avery Lanning and I'm working on Kalman filters. Kalman filters receive information from the various sensors on Little Pig, and they combine this information while taking into account the imperfections in order to produce a result that is greater than the sum of its parts. A good example is wheel odometry. Little Pig's wheel odometry functions just fine when it goes in a straight line. But because Little Pig uses the same sort of steering that's in a car, whenever Little Pig turns left or right, one of the wheels slips. And it produces an odometry value that doesn't quite match the amount of distance that it actually traveled. You can see this on the right. Whenever Little Pig moved around, it saw the wall in a different place each time because its odometry had slipped. And it kept mapping out where the wall was and kept getting confused or lost. This is why the information from the sensors are fused. You can see this here. Left is what it should be. The red's where Little Pig's currently seeing, the black is where it is mapped out in the past. The right is problematic. You can see here, there are three different instances of the same car. Little Pig saw the same car 3 different times, and as a result of its bad odometry, it kept thinking, hey, this must be a different car because it's in a different location. So now Little Pig thinks it can't move through here because there are 3 cars here, when it really should think there's one, and it should be able to move through there, just drive around that one car. Getting Little Pig's Kalman filters working requires tuning a covariance matrices. That's really what the heart of it is. It's a 15 by 15 matrix that determines how much to trust each sensor and how much each one should vary or become just trustable to a certain degree as a result of the variance of another one. The result allows Little Pig to accomplish a task called localization in order to know where it is relative to its surroundings. And localization is very important for the next package, TEB. Localization is necessary because Little Pig cannot go from where it is to where it needs to be unless it knows where it is.
Hello, my name is Jesus Villagrana, and I will be giving you an overview about TEB Local Planner and how the package was implemented within our project. TEB is time elastic band that will create a trajectory for Little Pig when given a navigation goal to reach. While Little Pig is trying to reach the navigation goal, it will use the global and local cost maps. The global cost map will make a waypoint route for Little Pig to reach its end goal. On the other hand, the local cost map will consider obstacles that it finds in the text and will create new waypoints while taking the obstacles into consideration. The way Little Pig can detect the obstacles in the simulation is by using the lasers that are provided with it. Packages that we used to accomplish TEB in the simulation were TEB Local Planner, Move Base, and Navigation. As you can see in the simulation, there is a path that Little Pig is taking. It is the green line. The red line that's over it is showing the indication of the best waypoint with the lowest cost map. The red spots around the map are obstacles that the lasers were able to pick up, and as you can see in the left corner, there is a camera that is also showing you the obstacles that are around the area. This is the work that we have been able to accomplish in the simulation with TEB Local Planner and its packages to implement for our project.
Hi, my name is AJ Hennessy, and my work on Little Pig has been primarily focused on transform frames. The transform frame package lets the user keep track of multiple coordinate frames over time through broadcasters and listeners. I made broadcasters and listeners for each of the frames listed. The way they are listed is how they appear in the transform frame tree, meaning base link is connected to chassis, chassis is connected to laser link back, IMU link, and camera link. Which this also means that there's a broadcaster and a listener between those 4 frames connected to chassis, and a broadcaster and listener connected from chassis to baselink. I followed Rep 103 for the units and coordinate conventions, meaning length is in meters and time is in seconds, and Rep 105 for the naming and structure of my transform frame tree, meaning I chose to use the names baselink and chassis respectively. The robot state publisher package handles the frames listed. It uses the description specified in our URDF and the joint positions from joint state publisher to calculate the forward kinematics of the robot and publishes the results via transform frame. All the frames listed are also connected to chassis itself. Now, this can all be better understood through seeing the transform frame tree itself. So as I mentioned, we track multiple coordinate frames through broadcasters and listeners. For example, if there's a broadcaster for the transform from ODOM to baselink and a listener to receive that transform. This continues on from baselink to chassis, and then chassis to many other frames. From finding the transform, we can find the relative position to whatever the frame in question is connected to.
Hello, I'm Harel. I'm a computer science student, and for this project, I was tasked with learning about, diagnosing, and improving the communication between our computer and our motor controller. This communication is done through what is known as a controller area network. This is similar to a computer network and is often found in cars and planes and many other robots. I was able to work on several issues surrounding this network. The first issue I worked on was knowing which motor to talk to. So the original software package we had was only designed to talk to one motor per controller. I was able to improve on the software design from the previous team and fix this so that the computer knows which motor it is talking to, whether it's the steering motor or the propulsion motor, which in our case are both on the same controller. The next issue I was able to work on was motor operating modes. So the motor controller can put the motor into many different modes depending on what we want out of the motor, whether it's a position for the steering motor or a velocity for the propulsion motor. This is important because we need to know which commands to send to the motor, whether it's radians or RPM or something else. The third issue I was able to work on was odometry reporting. So we use sensors on each motor to report back where the motor is and if the motor is doing what we want it to do. We then use that information to get an approximation of how far the robot has traveled since it started, and we can feed that information into our other sources of odometry, such as common filters, to get a good approximation of where we're at. Finally, we need to know if something is wrong with the motor, such as it drawing too much power, or if one of the sensors has failed, which is known as a loop error. We can then report that back and shut the system down safely, and then use that data to improve our design. Finally, as a computer science student, I had the opportunity to learn about very complex software packages and break them down into their individual parts and improve the design as I saw necessary. This is challenging work, but is always rewarding to see code that you've written on the screen be translated into a real-world product.
Hello, I am Clayton Dickerson, and I did the computer vision and follow mode for Lil Pig. Computer vision and follow mode is handled through MATLAB and Simulink, primarily using the computer vision toolbox and ROS toolbox. The current computer vision code that we have is object detection, where it finds a specific object in an image, blob analysis, where it finds a cluster of a specific color in an image, and camera calibration, where it removes distortion from a camera in order to improve computer vision accuracy. Follow mode is an alternative autonomous navigation mode for Lil Pig. In follow mode, Lil Pig will track an object that it sees on camera and attempt to follow it. It will continue to track the same object the best it can, despite things like the object moving off screen or the introduction of a second identical object. It will also use the lasers to check if it may run into a wall and instead attempt to avoid it. To better demonstrate follow mode's logic, here's its model in Simulink. A ROS subscriber block takes a camera image. That image is then read, sent to a blob analysis code, and then once that code finds a blob, it exports the blob's X, Y, and size. Those values are then given to a video display alongside the original image in order to display the result that it got. The blob size is used to determine speed. If the object is too small in an image, then that means it's too far away and Lil Pig speeds up. If it's too big in an image, that means it's too close and Lil Pig backs up. Similarly, X is used to determine steering. Steering is overwritten, however, if the lasers detect an object that is too close to the robot, and the robot will instead try to steer away from the object in order to avoid collision. Once everything is calculated, a twist message is then constructed, and then sent to the little pig in order to drive it.
In order to make it so that the simulated testing environment will be easily accessible for future parties working on Little Pig, an install script is created. This should install the robot operating system, gazebo, and RViz in their relevant capacities in order to support the Little Pig testing environment. This version of Robot Operating System, or ROS, that we are using is constrained to a specific version of Ubuntu. This makes writing a script to assemble and establish a working environment somewhat simpler, because everyone has to be running at least that base version of the operating system in order for it to work correctly. Of the three main software systems that users have to interact with, Robot Operating System is the one chosen to control Little Pig, and it does this through a nodal design in which packages are passed from one node to another in order to communicate in such a way that nodes can be removed or added as needed for different functionality. Gazebo provides a testing environment in which the robot and its environment is simulated. And finally, RViz allows us to visualize sensor data in a meaningful way. The script initially installs ROS and makes the necessary changes so that the operating system is able to download packages related to ROS without any further configuration. It then clones the required repositories stored remotely with GitHub, one for each major portion of the project, and then the script installs the necessary package dependencies for each of those. After this, the user should have a testing environment in which they can pursue further development of the Little Pig robot.
Little Pig is a UGV, an unmanned ground vehicle, developed by and for the U.S. Air Force. Some tasks that the U.S. Air Force has for Little Pig is they want it to drive the perimeter of the base and check for breaks in the fence line, scan license plates, and chase birds off the runway or check for any other obstructions. Little Pig navigates using odometry. Odometry allows you to find your position in a 2D space by knowing the initial position and tracking the change of position due to velocity and the direction of the robot. LiDAR and cameras are the sensors that allow Little Pig to navigate in a rapidly changing environment and avoid obstacles in the environment. We use a GPS to validate the odometry calculations. Little Pig also has a Pixhawk drone controller that will be used for long-distance communications with it. Here we have a schematic of how all of Little Pig's hardware is connected. We have a 58.2 volt 40 amp battery, which is developed from Tesla battery cells. This powers a 1.5 kilowatt drive motor and a 300 watt steering motor. The sensors are all controlled by an NVIDIA Jetson TX2 computer. This is what processes the sensory data and tells the motors where to go.
So this is the new steering system. This steering system comprises of a new motor from Midwest Ocean. This motor is mounted to a mounting plate that has been welded and folded by us. The motor connects to a coupling that has a shear bolt installed on it. The shear bolt is to protect the whole system just in case of any over torques. The shear bolt would break and protect anything else from breaking. The drive shaft then connects to a spline on the rack and pinion, and that rack and pinion turns the wheels. The rack and pinion is held in place via that little angle iron piece you can see in the bottom left corner. This is what we hope to, and we've added actually C-clamps later to prevent any sliding of the rack and pinion left to right. That became more of a concern as we later on realized how much torque that rack and pinion is undergoing. For testing reasons, we've wanted to evaluate the drive torque in the steering. These are theoretical values, but the max degrees of incline we can't actually calculate that yet because we haven't been able to get Little Pig properly weighed. For the thrust, we calculated it to be 67.8 pounds and the top speed about 11 miles per hour. The steering on Little Pig is adequate. We noticed that there's a little bit reduced range of motion for the left-right turning. We can increase this by moving the rack and pinion towards the front of Little Pig, but this would increase the stress on the rack and pinion, and I don't know that this rack and pinion that we have is strong enough for that. So that'll be something for teams in the future to look forward to changing. For future recommendations, we do recommend a new drive motor and motor controller. The drive motor needs a higher kilowatt value. The current motor is only 1.5 kilowatts. We need a 30 kilowatt motor to have enough torque to resemble what an ATV could actually do. For the motor controller, we need a higher nominal current. The current motor controller has a 70 amp nominal current. We need more around 400, and that's to power the stronger motor that we want. Some of these diagrams on the right are just sketches and drawings of the math that we did to calculate all this. Here's a video of Little Pig driving around. Currently, we're controlling it with an Xbox controller through USB to the motor controller. We've got ROS working, but we have run into some CAN bus communication errors, and it actually has nothing to do with ROS really or the motor controller. It's just something low level on the Ubuntu to CAN interface with the motor controller. We have been able to turn those errors off and get it driving around fine, but we need to figure out what's wrong with those errors to really continue moving forward. We've temporarily been able to disable them and just drive around, but it hasn't been working very well. But I think that's the story for Little Pig.